So let's talk about vertical circles. Since I didn't do such a great job in my lecture during class, let's unpack this a little bit. A great example to use to discuss vertical circles is amusement park rides, because they're very visceral. Your body knows what this feels like. Particularly, my body does not appreciate how this ride feels. This is called the Enterprise, this one right here. And the first and only time I rode this, I did not enjoy it for reasons which will become apparent in our discussion. Let's start at the top and the bottom of the ride. These are maybe the most useful points, certainly the most different from each other along the sequence of the ride, and also the easiest to analyze, actually. So at the top of the ride, here is a person, and they have both their weight downward and, because the seat is underneath them, well, the seat is touching their bottom, which is now above them, the seat is providing a normal force downward against them. Whereas for the folks at the bottom, the seat is underneath them, and so the normal force between them and the seat is upward, but mg is always, as it is, downward. So at the bottom, we've got this for our free body diagram. We've got a normal force upward and mg downward. And for each of these locations, the centripetal force is pointing towards the center of the circle. That is its nature. Centripetal acceleration is always directing you towards the center of the circle. And so the net force, the sum of any combination of forces, is directing them towards a circular motion, forcing them to continue in a circular motion. So for the bottom, the centripetal acceleration is upward. So for this case, at the bottom, we'll consider positive to be upward. And so we can create a Newton's second law statement for that. Upward being positive, so we can say normal force minus mg equals mv squared over r. Whereas at the top, the centripetal acceleration is downward. So let's call that positive for the moment that they're at the top. So we've got normal plus mg equals mv squared over r. So I'm going to put a little star next to both of these, because this is essentially the starting point of any good vertical circle discussion. Also, at this time, I would like to emphasize how in love the AP exam is with vertical circles. Be really good at vertical circles. We're going to see these again and again and again. They're going to show up all over the place. And so really let this, really get into this. All right, so starting from a point where we have expressions for the top and bottom forces, let's consider this thing that we're going to call critical velocity. You may have been on a ride where, like typically roller coasters do this really well, not during the loopy part, but when they're going over the whoop-de-doos, you might feel a moment where you just lifted out of your seat. You just feel like you've just barely lost touch with the seat that you're sitting on. And it's also possible to do this in a vertical circle. Recommend doing something like this, holding a pen and whooping your hand back and forth. And if you go ever slower, you can feel just a moment at the top of that circle where the pen just seems to lose touch with your fingers, but doesn't actually fall away. It's just kind of coasting adjacent to your fingers before you catch it on the other side. And that moment is what we call the critical velocity. Your hand is moving at a very specific velocity for an interesting thing to happen. And the moment where the contact is broken between your fingers and the pen, is the moment when the normal force becomes 0. So let's consider what's going on in this situation at that moment when the normal force becomes 0 at the top of the ride. So if the normal force becomes 0, then what we're left with is just mg equals mv squared over r. We cancel the m's, and it turns out that g equals v squared over r. G equals the centripetal acceleration. The amount of acceleration that is present at the top of that curvature is exactly equal to gravity. So the object there is going to fall away from your hand at the acceleration of gravity, but your hand or the seat or whatever it is also accelerating downward at exactly that same rate. So basically they're accelerating downward together, basically in a tie. So one is not catching up to the other, one is not falling away from the other, and they're basically just moving adjacent to each other. And that's why it seems to float right next to the surface. So if that's the case at the top, what's going on at the bottom? Well, if the centripetal acceleration is equal to g at the top, well, it doesn't matter where you are, the centripetal acceleration is equal to the centripetal acceleration. So if we plug that value in at the bottom, assuming you're going at the same speed as you would in a ride, because they're fixed, rigid mechanical objects, that every part's going to be going the same speed. And so if we plug in g for that centripetal acceleration, at the bottom, the normal force minus mg can equal mg. Solve for normal force. Normal force is going to equal 2 mg. So at the top, you're going to have the sensation of no normal force pressing into you, whereas at the bottom of this ride, you're going to have the sensation of double the normal force. And when it comes to your body sensation, what you feel, well, when you're sitting still at rest, I'm just sitting here on my chair, I've got a normal force up and mg down, and normal minus mg equals 0. When I'm not accelerating, my normal force is equal to mg. So basically, we could say I'm experiencing 1g, 1 times my normal weight. So when my normal force equals mg, that's me feeling my normal self, me feeling my normal weight. When the normal force goes to 0, that's going to give me the sensation of 0g. That's going to give me the sensation of floating. But when my normal force is 2g's, that's going to give me the sensation of being twice as heavy. And so this goes to explain why rides like this might not sit well for everybody, because like Mr. Mahaka's mustache, the normal force can vary anywhere from nothing to twice as much as what you would usually expect or usually experience. And so your stomach is going to go from floating to down in the bottom, floating to down in the bottom of your abdomen, and repeat that 20 times as the ride goes on, and you come off feeling a little green. So the last example I want to take a look at is the top versus the bottom at any velocity. So what we just described was this critical velocity, the critical velocity when the normal force goes to 0. But not every ride has you floating in your seat as you crest the top of the circle. And so let's consider what happens top versus bottom at any velocity. Looking up the Enterprise online, I was informed that at the bottom, the Enterprise is giving you the sensation of 3g's. So at the bottom, we'd say that the normal force is 3 times your weight. You're having the sensation of being 3 times heavier than you usually are. And so let's take that, we got mg down, normal force up, normal force minus mg equals mv squared over r. But in this case, the normal force is 3 times what you would normally feel. So 3mg minus mg equals mv squared over r. Cancel all those m's. 3g minus g, so that's 2g equals v squared over r. So the centripetal acceleration is 2g. It's not how you're feeling. You are feeling 3 times your normal weight, because the normal force essentially dictates how you feel. But you're actually undergoing 2 g's of acceleration. And because this ride is rigid, and you're going to be going the same speed at the top as you are at the bottom, the centripetal acceleration at the top will also be 2g. So at the top, let's find out what the normal force will be on you at that point. Normal plus mg at the top equals mv squared over r, or mass times centripetal acceleration. So we got normal force plus mg equals mass times 2g. All right, so that gives us 2mg on the right, normal plus mg here, minus an mg from both sides. So that leaves us with a normal force equals mg. Oh. So on the Enterprise ride, where you might feel 3 times your normal weight, 3 times heavy, at the bottom, at the top, you're actually going to feel actually normal. You would feel as though you were just standing on the floor, assuming you could sustain that sensation for any length of time. I regret using the word normal here because I'm not referring to the normal force, but I'm referring to your normal feeling of weight. And so the Enterprise ride varies from 3 G's at the bottom to 1 G at the top. And something you might notice: 3 G's at the bottom, 1 G at the top. On the critical velocity example, we had 2 G's at the bottom, 0 G's at the top. Anything you notice? If not, I'll tell you. 0 to 2 is a difference of 2 G's. 1 to 3 is a difference of 2 G's. So on any circle that where you're traveling at a constant velocity everywhere in the circle, you're going to feel a 2G difference between the top and the bottom. It's just an interesting little side note. And that's what I have to say about vertical circles. Thanks for watching.